Hi everybody, I hope this video finds you well. Today we're going to be finishing up section 2.6 from your textbook, talking about some properties of the inverse. In the last two videos we sort of established a condition on the rank of the matrix that will tell you when a matrix does have an inverse. We saw that a matrix must have full rank. In other words, its rank has to be equivalent to its number of rows and its number of columns to actually be invertible. And we saw that that was an if and only if condition. And then in the previous video, we actually went computationally through a process where you augment a matrix with the identity matrix and then use elementary row operations to change the matrix into the identity matrix. And then what the identity matrix becomes is actually your inverse. Now, in this video, we're going to talk about some properties of this inverse, and namely sort of how it relates to some of the other operations we've studied. So these are three sort of major properties of the inverse here. So for this, we're going to let A and B be n by n invertible matrices. Okay, so we're going to assume that we have these two invertible matrices of the same size. So property number one, A inverse is also invertible. And we get that the inverse of the inverse is the original matrix. So this first property says that if you have a matrix A that is invertible, then its inverse is also invertible. So the inverse has an inverse. And as you would expect, the inverse of the inverse is the original matrix. All right, second property, AB is also invertible. So this tells you guys that the product of two invertible matrices is also invertible. So if you take the product of two things that are invertible, then it will be invertible. And it tells us what that inverse looks like. So the inverse of a product is the individual inverses, but with the direction, sort of the order of multiplication reverse. So the inverse of A times B is actually B inverse times A inverse. Finally, we've got a property that sort of explains how inverse works with transpose, which is one of those sort of operations that was specifically for matrices. So A transpose is also invertible. So the transpose of an invertible matrix is also invertible. And the inverse of the transpose is the same as the transpose of the inverse. So in other words, inverse and transpose actually commute, right? So if you're taking the inverse of the transpose, you can do that as the transpose of the inverse, whichever sort of order you prefer here. Now, all three are proved in textbook. So we won't go through a proof of each of these, but we'll just pick one. I don't know, since we're going to do something with it in just a moment, we'll go ahead and prove number two here, right? So you can see proofs of all three of these in your textbook if you want. So proof of property two. So what we need to do is, we need to show that AB is also invertible. So we get to assume AB invertible. We need to show that AB is invertible. All right, so what we're going to do, right, and we're going to use this sort of property here, right? So what we need to show is that AB and then times this sort of potential inverse here, B inverse A inverse, is going to be the identity. And the other direction, that if we do B inverse A inverse, let's put some parentheses around that, and then go to our matrix AB, then that will be the identity matrix. All right, so remember, when you're trying to show something has an inverse, right, what you need to show is that no matter which side you multiply it on, you will get back to that identity matrix. So let's go ahead and do that. AB and then B inverse A inverse. Well, we know that matrix multiplication, while it is not commutative, is associative. So we can just drop those parentheses. So this is AB, B inverse, A inverse. Then, of course, B inverse. Well, we know that B is invertible and it has its inverse. So we can just write that as A, I, N, A inverse. And then we can say, well, since that's A times the identity matrix, that'll just be A, so A inverse. And then that, of course, is the identity matrix. So we're good on that one. Let's check the other direction. So now we need to start with B inverse A inverse and multiply that by AB. Once again, matrix multiplication is associative, so the parentheses are unnecessary. B inverse AB. Okay, we start with these sort of middle two, A inverse A, so we can make that B inverse identity B by definition of A inverse and A. Then, of course, this is the inverse matrix, so you could mix it with B inverse and just call it B inverse, or you could mix it with B and just call it B. Either way, we should get B inverse B, and then, of course, by definition, that is the identity as well. So that shows us that if we take the product of two invertible matrices, then the result will also be invertible, and the inverse of that result is the opposite product of the individual inverses. Okay, so that was pretty nice and easy there. What we're going to do on the next page is actually extend property 2 to an arbitrary number of matrices rather than just having a product of two matrices. So let's do a quick follow-up to this. So follow-up. We're going to show that if A1 all the way down to AN, let's not use N, let's say AK, are all N by N invertible matrices, then the product A1, A2 times dot 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 times AN is invertible with inverse A1, A2 down to AN. Inverse is AN inverse, A2 inverse, A1 inverse. So in other words, this extends property 2 that we just proved to an arbitrary number of matrices. So to prove this, because it's an arbitrary number of matrices rather than just a pair of matrices, we're actually going to need to use a proof by induction. So proof by induction. All right. So we have a base case, right? We could choose the base case to be n equals 1 or n equals 2. Probably since we're talking about products, it makes more sense to start the base case at n equals 2 here, where you actually have a product. So base case n equals 2. What we would need to show is we need to show A1, A2. We need to show if A1, A2 are invertible, then A1 times A2 is invertible with inverse A2 inverse A1 inverse. Now, do we need to do much to do this? Well, no, because this is for two matrices, and we just did that in the previous one. So, let's put our little proof there. Proof just showed this. Okay, so we don't need to do anything for the base case because the base case of having two matrices is what we already just showed. So now we're going to take our sort of inductive step. So we're going to assume that if you have A1, A2 down to some AM, all invertible matrices, then A1, A2 times dot 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 times AM is invertible with inverse AM inverse dot 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 A2 inverse A1 inverse. What do we need to show then? Well, we need to show this holds for A1 down, I've been using A2 there as well. A1, comma, A2, all the way down to AM, and then another one, AM plus 1. All right, so let's go ahead and do that, right? So what we're going to try to do here is we need to show that this holds for this set of matrices, right? So this means that we need to show that this guy here, so we need to show that the product A1, A2, AM plus 1 is invertible with inverse AM plus 1 inverse, AM inverse, A2 inverse, A1 inverse. So we'll actually prove this on the sort of next page here. So let's go ahead and give ourselves one more page to do this, right? So let's do our proof here. All right. So let's go ahead and consider A1 times A2 times times AM plus 1 inverse. Okay. So what we're going to do is we're going to sort of group this. We're going to group all of these together with this guy as sort of separated. So now we have two sort of matrices. This giant product here is treated as one, and this giant product here is, in this single matrix here, is treated as the other. Now we know that this is equivalent to AM plus 1 inverse, and then A1, A2 down to AM inverse. How do we know that? Well, that's just simply because, right, of our sort of base case, right? This, we know that if you invert the product of two invertible matrices, you just sort of reverse the order and take the inverses individually. But what can we say about this? Well, this is that inductive hypothesis, or that inductive step. So we can say that this is AM plus 1 inverse, and then this guy, that inductive assumption holds. So we can say that that's AM inverse, A2 inverse, A1 inverse. And that was by the inductive hypothesis. And if you notice, that's exactly what we wanted to show. So QED, and we're all good. So what we've basically shown is that if you have a giant product of invertible matrices, then that giant product will also be invertible, and its inverse is by inverting each of the matrices individually and reversing the order of multiplication. And we did that as a nice little proof by induction. All right. Let's go ahead and, since we sort of introduced these properties, and even though we sort of got hung up on the one about multiplication here, we did bring up a nice sort of little thing about how the inverse and transpose work. So we're going to just take a moment to talk about a very sort of special type of matrix for a moment. So we're going to give a quick definition on what is called an orthogonal matrix. So a square invertible matrix A is said to be orthogonal if A inverse is equal to A transpose. So you call a matrix orthogonal if it's an invertible matrix that has the special property that its inverse is its transpose. So let's see a quick example of one of those. So an example is, let's try to decide, is the matrix A equals, it'll look a little weird, so we'll do root 3 over 2, 1/2, negative 1/2, and root 3 over 2, an orthogonal matrix. Well, we could analyze this question in several ways. We could use our inverse process to figure out the inverse of this matrix by augmenting it with the identity and then using elementary row operations. Then once we got the inverse, we could check if the inverse is the same as the transpose. But we could also check this by more simply figuring out the transpose and then seeing if the transpose acts as the inverse. So let's try that, right? Let's note that A transpose here, if we do the transpose of that matrix, remember transpose takes the row and makes it the column. So we get root 3 over 2, 1/2, and then second row would become second column, minus 1/2 root 3 over 2. Okay, so now let's check. What happens if we do A transpose, which is root 3 over 2, 1/2, negative 1/2 root 3 over 2 times this transpose that we just figured out, root 3 over 2, negative 1/2 root 3 over 2. So we take a row times a column. Looks like if we do that, we should get 3 over 4 plus 1/4, which is 1. Then this row times this column, looks like we should get negative root 3 over 4 and root 3 over 4, which is 0. Then this row times this column, looks like we'd get negative root 3 over 4 and root 3 over 4, so that would be 0. And then this row times this column, which would be 1/4 and 3 over 4, which would add up to 1. So we're all good with that. Now we need to check the other way. A transpose A is, well, let's go ahead and see. So A transpose was root 3 over 2 minus 1/2, 1/2 root 3 over 2, and then root 3 over 2, 1/2 minus 1/2, and root 3 over 2. So we take this row times this column. Looks like we should get 3 over 4 plus 1/4, so that is going to be 1. Then this row times this column, that's going to be root 3 over 4 minus root 3 over 4, which is 0. This row times this column, looks like we're going to get root 3 over 4 minus root 3 over 4, so that's going to be 0. And this row times this column, which is going to be 1/4 and 3/4, which is going to be 1. So there we go. So that shows that this matrix has the transpose is the same as its inverse. So A inverse equals A transpose, which implies A is orthogonal. So this is just sort of a nice special type of matrix that has this property that its inverse is the same as its transpose, right? Obviously, most matrices out there do not have this property. Remember, a lot of square matrices don't even have inverses, but this is a very sort of special subclass of invertible matrices. These are ones that's transpose and match their inverse. All right. We've got one more sort of major property to talk about the inverse, and it actually sort of relates to this check that we did here. It sort of seems unnecessary over and over again to have to check that on both sides of the multiplication, things work out. Now we know to be careful about the direction of multiplication because matrix multiplication is non-commutative, but we're actually going to show that in the case of inverses, only doing one of these checks is actually sufficient. So we've got another theorem that sort of does that for us here. So let's go ahead and take a look at that. So for this theorem, we're going to say, we're going to let A be, let's see, we want to say let A times B equal, so I guess we should give some sizes here just to make sure. Let A comma B be n by n matrices such that AB is equal to IN. Then what we're going to say is then A is invertible and A inverse is equal to B. So what does this theorem say? Well, what this says is that if you have two matrices and you multiply them together and get the identity, even if you only do the multiplication on one side, so you're not checking both AB and BA, you're only checking AB, then that other matrix B really is the inverse, even though we only showed that on the right-hand side multiplication, you get the identity matrix. So we're going to go ahead and prove this guy. So proof. What we're going to do is we're going to start with, well, our assumption AB equals IN. Okay. So what can we sort of do with this sort of matrix? Well, we're going to sort of start with a sort of column vector. So let B be any column vector of size n. And this is pretty standard. As you guys know, whenever we're trying to do these sort of abstract proofs about the inverse or about, sort of matrices in general, we often start to use one of these column vectors so that we can reduce things into the system of equations that we're more comfortable with. All right, so let's consider AB times B. Well, what do we know about that? Well, we know that AB is the same as IN, the identity matrix times B, which is the same as B. So we can say that AB times B is equal to B. Okay, not particularly interesting. But let's go ahead and do a clever sort of grouping with this. Let's regroup this as, let's consider this as A, B, B equals B. So notice what this means. This means that for any B, the system AX equals B has a solution. So that means that this system has a solution, at least one solution, namely B times little b. So what we've just figured out there is that any system involving this matrix A with coefficients, that doesn't matter what this sort of B value is here, it will always have at least one solution, namely this sort of B value here. This means, though, since B is any size n, right? This is true for anything in sort of Rn, right? Any column vector of size n. Then rank of A must be equal to n, right? What this is saying is that since this system will always have a solution, you can't have a rank that's less than n. If you did have a rank that's less than n, there would be some choice of B that would be inconsistent. And we know that because if your rank was less than n, then when you augment it with B, you'd be able to choose a B that would give you a higher rank. But we know that all of them always have a solution, so the rank must be full here. So by that sort of previous theorem, right, by the previous sort of big theorem, rank of A equals n, that implies A is invertible. Remember, that's the sort of big idea that we've introduced in this section, that if your rank is full, then the matrix is automatically invertible. So we've now shown, right, that A is invertible. Now we need to show that it has this inverse. Well, let's try to do that. Let's consider, so now consider A inverse. So what can we say about A inverse? Well, A inverse sort of dumbly is A inverse times the identity. And if you think about that, well, by this sort of property up here, we assume that AB is the same as the identity matrix. So we can replace that identity matrix with AB. Now we can do a little grouping and say, okay, A inverse in A, that's the same as the identity matrix by the definition of the inverse, times B. But what's IN times B? Well, that is, of course, just B. So what have we shown? We've shown that A inverse is indeed B. So A inverse does equal B. All right, what's the big takeaway from all of this? What this shows you is that now that you guys know this theorem, if you need to check that something is an inverse, you only need to multiply it on one side and get the identity matrix. So if we had done this whole thing earlier, when we did this previous example, once we did this, we would have been done. We would have said, oh, I multiplied A transpose and got the identity. That means A inverse is the transpose. We wouldn't have needed to do the second piece. In other words, it would cut all those sort of checks in half. So this is a sort of important theorem just in terms of checking inverses here. All right, we've got one sort of nice little follow-up with this. So one quick little follow-up here. The last thing we want to say here is that this is sort of a reverse of one of the first properties we discussed. So if A, B are n by n matrices and A times B is invertible, then A and B are invertible. So what this theorem says is if you have two matrices and you don't know anything about whether or not they're invertible, but you know that their product is invertible, then you know the individual components are invertible. Now, if you go way back to where we started, the reason I sort of call this the sort of reverse is that we said that if you have individually invertible matrices, then the product is invertible. Now we're saying that if the product is invertible, then each individual matrix is also invertible. So it's sort of the reverse of this property 2 here. So let's go ahead and see how we would prove this. So We know, as our sort of proof here, we know AB is invertible. Okay? Let's call its inverse AB with a little inverse. Now, it is super tempting to say, okay, I know what to do here. I take this guy and I just distribute it onto each piece and I switch the order. Unfortunately, that assumes that these are individually invertible, but we actually don't know that. That's what we're trying to prove. So this is the best we can say for its inverse. We can just call it AB inverse. So now what I'm going to do is I'm going to claim that A inverse actually equals B AB inverse. Let's see if that's actually true. To check this, let's do AA inverse. Well, AA inverse is going to be AB AB inverse. But by definition, AB is invertible and its inverse is AB inverse. So this whole thing here, that has to just be the identity matrix. Well, normally we would then need to show that A inverse times A gives us the identity matrix. But by previous theorem, this implies A inverse is the actual inverse. We don't need to do anything else because we just showed in the previous theorem, as long as you sort of do it on one side and you show that it becomes the identity matrix, that is sufficient. Okay, let's claim that B inverse is going to be AB inverse B, A. AB inverse A. So to check this, what we'll do is we'll go ahead and use B inverse B, and that would become AB inverse A and then B. And then, of course, well, you can see that this is the inverse of this right here. So we can say that that is the identity matrix. Well, but by the previous theorem, this implies that B inverse is actually the correct inverse of B. And that's what we wanted to show. So this is a nice sort of reverse of that sort of second property that said that if you have individually invertible matrices, then their product is invertible. This just simply says that if the product is invertible, then the individual components are also invertible. So this will do it for section 2.6. We'll be skipping section 2.7. So the next video you guys will see will be on section 2.8, which actually finishes up chapter 2 entirely.